Okay, no, Teams is okay. Yeah, these are the issues like inviting other people. नहीं, तुम लोग का YouTube channel है, अच्छा है. तो
Right.
invite करना बड़ा मुश्किल है किसी third party.
So Hemanto, it is broadcasted on YouTube channel also, right? Hemant?
उसका mic off है. So Hemant is a colleague of yours?
No. He is a staff. He's taking care technical staff. Yes. So I got the reply. Yes, sir. Yes. Rupam replied.
Good. तो मैं chat box नहीं देखूंगा. I'll just focus on my talk. So
No, it's fine. If something comes, I will inform you on chat box.
yeah, actually question answer time will take unless there is a somebody you interrupt and ask some question.
No. It's fine. So chat box you won't have to look at. After talk, you can have a look.
That's fine.
I don't know. Saurabh was supposed to join. He is at home.
I see. Okay, we have a lot of time. अभी 4 मिनट तो आई है. 4 मिनट के बाद. ये अभी काफी ठंडा हो गया. What is वहाँ का टेम्परेचर कितना है अभी?
हाँ, थोड़ा ठंड है इधर भी.
अच्छा.
तो सौरभ ज्वाइन कर रहा है. Okay.
Good. So I'll say hello. So who is the head right now?
Professor Subhadeep Ghosh.
Hi, Saurabh. You can hear me? Saurabh, he is muted.
Hi, Mahendra, how are you?
Good. You? Happy New Year.
Happy New Year. Good to see you.
Yeah, me too. Virtual. Everything is virtual these days.
Everything is virtual. That's right.
How is life?
How's? Yeah, things are okay. How's it in Kanpur? Is it cold?
Yes, I think today was some maybe 5-6 degrees. It was quite cold.
Oh,
Minimum.
Okay.
Morning there was fog till 11:30.
Okay.
Still cold. I put the heater on in the room.
Okay.
Yeah.
Are you in the same room as earlier?
In the office, no, I'm right now at home, but yeah, my office is the 4th floor office. I mean, I don't know whether you saw me in 4th floor or 3rd floor. I moved to 4th floor in
4th floor. Yeah.
Tulsidas, Tulsidas office.
Oh, in that office you have taken. Okay. That was just opposite to where we used to sit.
That's right. I'm opposite that. Yes.
That's
so
right.
there is bigger room and also private. Well, somewhat. This my earlier office was very close to classrooms and all. No? So it was corridor.
That's right.
So you guys have pretty nice office. I saw Pankaj's office. You are in the same building.
I am not. Pankaj is, sort of luckier guy. So I am actually in the older building. And it's not as fancy as his office, but nevertheless very spacious.
Good. Yeah. So yeah, his office looks very fancy. So rather
no, fancy, but it is not user friendly. So it didn't have good ventilation.
Oh, I see.
Don't crib. But else I'll take your office. You can take mine.
So what are you teaching, Saurabh?
Right now I'm not teaching anything. See, what happened is that because of this COVID, there was theory courses that have been pulled in from this semester to the earlier semester.
I see.
So where I taught this elective course on condensed matter physics. So that course is no longer there. So I'll be taking tutorial because all these first year courses got shifted.
Yeah,
it's a mess actually. I don't know how we are going to come back to schedule.
So July will be fine. Let's hope. Yeah.
Let's hope July would be fine. This first year classes would still be staggered by about a month maybe, because July 3rd is when the this thing is your JEE advanced.
Oh yeah, I see.
So after that, about a month, then counseling and so on. So it'll still be, but we'll slowly get back to the normal schedule.
Yeah.
So JEE advanced is being
it's announced July 3rd. Yes. That's
okay. So unlike not in May.
Not in May. 2 months delayed.
CBSE shifted.
Yeah.
I think the board exams are shifted. So basically.
Yeah.
So should we start or wait for some couple of minutes?
Okay.
Yeah, just wait for a couple of minutes.
Okay. No, thing is that I have kept it open, so a lot of requests are coming, and then I need to switch to accept the request.
Yeah, that's a team fair. Well, both Zoom also like this. So good that you have colloquium, quite regular colloquium. We don't have yet.
Yeah, I mean, given that we are like IIT Roorkee, you must have got that mail, right? So basically, they're getting the Tony Leggett's was on 9th, 13th is Duncan Holden, then Charlie Kane sometime in February. Then a lot of others. I'm not. I mean, they're high energy people and all that. So they are. This is a time to utilize.
No, I agree. No, definitely. So when can get connected to IIT Roorkee? I mean, just send me a host name so that I can. Is it on Zoom or is it on a link?
No, I'll give you that. I'll send you that link at MKV at this thing. I'll do it right now. So you have to register. There's a Zoom link. You have to register, and then 13th is 9th have already gone, but 9th is already gone. But the same talk Tony Leggett gave in this Deen Dayal Upadhyay College or some such.
So that INSA, rather not INSA or Academy.
That's right.
Yeah. Good.
Pankaj, you can start, I guess.
Okay. So Happy New Year, everyone. So let's begin the first colloquium of this semester, and it's a privilege to have today's speaker, Professor Mahendra Verma from IIT Kanpur. He didn't need much introduction because he's quite well known in turbulence community. But for our young audience, I would like to say a few things about him. That he completed his BTech in computer science from IIT Madras, and subsequently he joined University of Maryland College Park for PhD. And after completing PhD from University of Maryland, he joined IIT Kanpur in 1994, I suppose. And right now he is professor in the physics department IIT Kanpur. He is recipient of Swarna Jayanti Fellowship, Dr. APJ Abdul Kalam Cray HPC Award, and INSA Teachers Award. He is fellow of INSA and Indian Academy of Science. Professor Verma research interests include turbulence, nonlinear dynamics, high performance computing, and non-equilibrium statistical physics. He and his group have developed a spectral code called Tarang that can simulate variety of turbulent flows. So with this, I once again I invite Professor Verma to deliver today's physics colloquium on universal theories and multi-scale description of nature. So I hand over the forum to Professor Verma.
Okay, thanks Pankaj for the very kind introduction, and also thanks to my colleagues in IT Guwahati for inviting me. So it's real privilege and honor to give this colloquium. So and happy new year to everyone. So these are bad times, so we need happy thing from everyone. Okay, so this is the title of my talk. It's a general talk. I've been thinking about it for the last 5 years or so on general topics. And this paper is published, well, this is on Arrow of Time. The paper is on Arrow of Time. It's published in 2019. And so some other related papers. And so if you look at the front page, you'll find some more popular articles on multi-scale physics. So the 3 articles I wrote for web. Anyway, so let's start. So we have wide variety of natural phenomena, starting from very tiny scale, 10 power minus 15, 16 meters at quarks, atoms. Then we keep going up at higher scales. Then we get biology, then astrophysics, planets, and well, basically planetary, stellar, then astro. So it's really a huge range of scales. And of course, the dream of scientists, including biologists and astrophysicists, physicists, all to understand majority of this phenomena. And of course, I mean, there are quite a few advances in physics. We have made big breakthroughs, but still there are a lot of problems which are open. I mean, there are many things are not understood. So, like for example, one thing I will discuss today is arrow of time. My talk will go around this theme of arrow of time. So I will, but it turns out, so let's just proceed. There are various approaches to it, and I will only allude upon some aspects of this problem. So I'll play this movie. So this is a, well, clip of a movie, this Theory of Everything, and this for a purpose. So let's hear this, what this great face talking has to say.
So what next?
Prove it. Prove with a single equation that time had a beginning. Wouldn't that be nice, Professor? For one simple, elegant equation to explain everything.
Yes. It would indeed.
Thank you.
Okay, so you can see the script I've written down. One simple, elegant equation to explain everything. Well, that is one of the motto of many physics, and I will try to say that this is not quite well. I mean, according to me, according to many others, so they think that this probably is not going to work, and so this is a debate whether we can have one equation to explain everything, or we need macroscopic description, varied laws. And there's a very nice article by Anderson, More is Different, in 1972. And I wrote an article recently this year, this is in Transaction of INE. So this has different theme. This is on symmetries, but this I talk about basically a fluid description. How can you get, how kinetic theory and fluid, I try to contrast the two. Anyway, so some of these topics which I will discuss will be coming back to this topic a bit later. So my title says universality, so in fact, abstract I wrote thinking that I will cover more aspects, but universal laws was one such aspect. So I will cover briefly what we mean by universality, and which is very powerful theme. We want to explain a lot of phenomena in a single framework. And quite a bit of effort has been, especially in particle physics, to look at fundamental laws and try to derive things from fundamental laws, or get a single equation for the laws, for the fundamental forces. And that has been one of the major drivers. So I will just allude upon law of gravitation. So law of universal gravitation, universal law of gravitation. So Newton came upon this idea first. Later on, Einstein modified this law. But in textbooks, we hear that Newton got his idea when some apple fell on his head. But it turns out this is totally incorrect story. This is there in textbooks also. Pity, but this is not true. How Newton got this idea? In fact, he derived quite a bit of reasonably difficult mathematics those days, and he got this idea by Kepler's third law. So I will just just sketch, the basic idea of how he got the idea, how he came to this law. So Kepler's third law says that for planets going around the sun, t squared, the time period squared of this planetary orbit, is proportional to r cube. R is the distance from the planet to the sun. Of course, these orbits are elliptical, but for today's talk, I will just assume it to be circular. And Kepler derived all this stuff based on observations by Tycho Brahe, in fact, for Earth and the Mars, these two planets. And so this is a law, based on two data points, two planets. So given this law, we can find out what is the acceleration of the planet around the sun. Acceleration omega squared r. So omega is 1 by t, so it's going to becomes r by t squared. And so t squared is r cube. I just get this Kepler's third law, substitute here. So r by r cube is 1 over r squared. So acceleration of the acceleration on the planet around the sun is 1 over r squared. So it's in fact follows easily for circular orbit. The derivation for ellipse is a bit complicated, but we do it in our mechanics course. Is other way around. Assuming 1 over r square force, we derive elliptical orbit, but Newton worked it out in inverse problem. So given basically elliptical orbit, how to derive the acceleration or force. Now, so this tells us that force on the planet is 1 over r squared. But what about force on the objects on the surface of the Earth? Is it the same force? Now, to derive this, Newton is, these people are of course geniuses, there's no doubt about it. So Newton gets a brilliant idea that let's treat Earth as a central object instead of Sun as a central object. Let's treat Earth in the center. Now, two things are falling on the Earth. What are the falling on the Earth? Moon is falling on the Earth. Something going around is like falling, no? Because if it didn't fall, it will just go in a straight line. So it is falling on the Earth, and stone on the surface of the Earth is also falling on the Earth. So now, if 1 over r squared law is correct, then we can figure out if 1 over r squared law is correct, then acceleration ratio will be inverse of r2 by r1 squared, inverse of this distance ratios. So among this, so there are two acceleration and two distances, right? Distance of Earth Moon and distance of stone Earth. Well, stone Earth is basically radius of the Earth, because Newton derived that a spherical object can be treated as a point object sitting at the center of the Earth with the same mass, center of the spherical object with the same mass. Okay, so here the two distances were known to Newton. In fact, known from earlier times. Both Indians and Greeks supposedly knew the radius of the Earth as well as Earth-Moon distance. So these two are known. Acceleration of the Moon is also known. How? Because you know the time period of the Moon around the Earth, 28 days or 28.5 days. So the fourth quantity, A2, acceleration on the surface of the Earth for any object can be computed. And he did compute. There is a bit of historical ambiguity, but for time being, we'll assume that we'll ignore all that complication, and either it's 9.6 or 9.8. You know, it happened in several months, or some. It happened in steps, but we'll ignore that. From this, we can compute that is 9.8 meter per second squared. Okay. Now we can of course easily compute, but he computed it in those days. So now you can measure it on the surface of the Earth. Those days there were not many accurate clocks, so they used to use inclined plane for measuring accelerations, and it was measured. Some claim it was Newton, some claim it was somebody else, but was measured to be this. Now then we can after this we can conclude the force that acts on the planets due from the sun is same as what acts on the stone on the surface of the Earth. So there are two different class of objects that experience the same force. Then of course Newton makes a generalization that any mass in the universe will experience same force. So if you have two objects of mass m1 and m2, they will experience that m1 m2 by r squared, and the proportionally constant g, which he didn't know, but he estimated by very ingenious means, but that g was calculated later. Okay, but that was done after Newton. Okay, anyway, so this is one example of universal law of nature, and this was in fact beautiful. So I kind of like this, and I put that in my when I taught mechanics in the class. Now this was in 1687, so this was the law. Now of course, inspired by these ideas, people started working on other fundamental forces. Like one major thing is electric and magnetic force. No? So these are the two forces, and so Faraday and various people, Ampere and so on. But Maxwell gave the law which combines both electric and magnetic forces. And so Maxwell's equation is another example of universal law. For of course there are two of them which are combined. Now these two forces become one force, electromagnetic force, and that was combined with weak nuclear by Glashow, Salam, Weinberg. So in fact it turns out electromagnetic plus weak nuclear is one force, and we at different energies we see them different, but this is basically one force. It has one origin, and bit later even strong nuclear was combined to that, and this is a standard model. This is a framework. Of course there are a lot of things are unsolved in this, but this is the basic idea which people strongly believe that these three are unified in a single framework, and this is one of the major unification which has won many Nobel Prizes. Now this is a single framework for three forces. Of course right now there is a debate that can gravity be combined to this, and this remains an unsolved problem. Okay, we'll see whether gravity can be unified. Is it? Maybe it is not to be unified. We don't know. So string theory is one such attempt. There are other things like loop gravity and so on, but this is not my field. So, but this is just kind of an example which I wanted to cover today. Now, basically, from this, of course, people went on from this video clip, what we saw, that we can explain everything once we understand the fundamental laws. Now, it turns out even this people who propose this idea are not in big believer of it now. I mean, at least many of them, and they think that this complexity theory or so Anderson is one such. He wasn't the proposer, but he is one such critic, saying more is different. So if you put in more objects, more systems, then you get things which are not included in this fundamental forces. Okay, one example I can say is color. Color is not really property of an electron, but color emerges is a emergent phenomena. So that's one such example. So I will come back to it later from again for this theme a bit later. Now other unification, other efforts many of in the audience like Saurabh works on condensed matter physics. So phase transition, so this is all sorts of phase transition can be classified in a general theory by Landau, then Ken Wilson and Michael Fisher and so on. So this is one theory of phase transition. Then the materials, we have one theory which can explain lots of material. I'm here that there are materials like the modern ones like topological insulator and so on. They belong to a different class, but a lot of material we can do in using band theory. I work on, and Pankaj also works on this Kolmogorov theory of turbulence. This theory, though it doesn't cover all sorts of phenomena, but it's a nice theory for hydrodynamic turbulence, like fluid turbulence. This is a theory which works for all sorts of flows, like turbulence in aeroplane. Some of it is same as turbulence in the river or turbulence in atmosphere. There's certain commonality between this phenomena. And chaotic systems, if you classify chaotic systems, there's certain like band structure. Similarly, we can classify chaotic systems in this unified framework. Okay, and these are microscopic laws. They are not really. We don't start from quarks and gluons or electrons for this. So these are in some sense microscopic laws. But these are again unification efforts. We want to understand one framework to describe different phenomena. Now, symmetries play a big role in unification or understanding unified theory. So there are, I mean, everybody knows about this, but just for completeness, I am putting it here, that spatial translation, spatial rotation, symmetry laws, fundamental laws are symmetric under spatial rotation. So if I take two masses and shift them to some other place, then law of gravitation does not change, or even Einstein theory will not change. So spatial translation, spatial rotation, and time translation. So fundamental laws are supposed to be respecting these three symmetries. I mean, there's no violation of these symmetries yet, and they are also connected with conservation laws. So they are related to three conservation laws: linear momentum, angular momentum, and energy. Okay. Now there are additional symmetries. These symmetries hold without any violation so far, but there are other symmetries. There are approximate symmetries. One is mirror symmetry, so left-right symmetry. So laws are supposed to be symmetric under mirror reflection, but it turns out this is violated. In weak nuclear force, this is violated. Gravity and electrodynamics supports it. I will not really dig into it because this is another topic which can at least take 15 minutes to explain fully. So just take my word for it that left-right symmetry is valid for gravity and electrodynamics, which is our daily experience, when we see that. I will focus on this time reversal symmetry, which is so I will explain a bit more around time reversal. So forward in time and backward in time, the fundamental forces, those four forces, respect somewhat. There is certain violation for this. So it is an approximate symmetry. There is a violation of time reversal in fundamental force itself. Okay. So in basically connected to weak nuclear again, but it's more complicated than simple parity violation. But in fact, they are connected. They are called CPT: charge, conjugation, parity, and time. They all three violated, but together they respect symmetry. So this is called CPT. But that's again a topic for people who work on particle physics or some condensed matter physicists. But I'll talk more from multi-scale perspective. This time reversal symmetry. That is what I will focus on. I have one slide on mirror symmetry. Very simple idea, but I will explain that towards the end of the talk. Okay, so now let's get to time reversal symmetry. So as I said, these three forces, gravity and electrodynamics, which is we experience in our daily lives, and strong nuclear. Okay, they respect the fundamental this time reversal symmetry, which I'm going to explain in the next slide. But weak nuclear does not. Okay, but my emphasis is not on this Lagrangian of these forces, how they are, how much they violate. No, that's not my objective. I will focus on basically macroscopic description in from turbulence perspective, in fact, but I'll give some more examples. So arrow of time. So we know in our daily lives that, for example, I'm always age. I mean, I'm not going to grow younger. So though fundamental laws are symmetric, but there is certain arrow of time. There is a things move forward. Like we are going from 2020 to 2021. So that is, there is certain direction. Why? How does it come? What are the causes of it? That is arrow of time. Okay. So what is the controversy? So this is what I will describe today, and there are simple resolutions of this topic according to what I believe. Okay. So let's derive what. Well, let's not derive. Let's illustrate what is time irreversible symmetry. Okay. So let's start with Newton's law. Though we can also write down for Schrodinger equation as well as for Lagrangian description, but we'll just stick to Newton's law. So mass, an object of mass m is feeling acceleration with certain force, so mr double dot is force. Now if force is symmetric under t2 minus t, that means if the trajectory is following certain path, I go from 0 to capital time t, then there's certain force it experiences on the trajectory. But if I go back the trajectory, from t I go to 0, I can imagine that things go backward in time, suppose, then it will follow, let's suppose it follows the same trajectory, then forces will remain the same when it follows. Gravity, you can imagine that there's a trajectory. In fact, I have the example here. This trajectory is going from A to B, So suppose I'm here, I feel some force, mg. Now, if I do the reverse project, I go from B to A, then at this point, my force remains the same. Of course, gravity is a very trivial example where force anyway is the same, but imagine that it was a big projectile where it is 1 over r square force, not mg force. Then again, when it reaches here at the same point, this point and this point, force will not be changed at the same point. Okay? So if the force is symmetric under t2 minus t operation, then forward and backward motions are symmetric. These can be derived mathematically. There's no problem with that. So the idea is that if I go from A to B forward in time, at B, I make the velocity field flipped. So velocity field is pointing this way right now. Pankaj, can you see my arrow? My pointer is visible, no?
Yeah.
Yeah, okay, good. So my velocity field was pointing this way, like projectile, is going down like this. But if I just turn the velocity field, then it will come back to A. So forward and backward, if there's no friction in vacuum, this will happen. People have done experiments and they find that the backward trajectory for under gravity will be exactly same as forward trajectory. And the time taken will also be the same, both backward and forward. Okay, so this is known. So this is called time reversal symmetry for gravity. Turns out some particle physics, basically some decay laws, do not follow, they violate this. So it's a pretty complicated discovery that it turns out some decays, forward decay and backward, well, basically backward decay can't be done, but it turns out there is certain signature which is enough to show that the time reversal symmetry is broken in a decay process. So let's look at it another way. I want to motivate my idea further. I will say that another example, a pendulum, it goes from left to right. Then we can also, the pendulum at this point, it comes from right to left. Now, in some sense, you can say this is forward motion for one cycle, and this will be backward motion. So for pendulum, definitely forward and backward motion are equally probable for pendulum. Of course, for complex systems, it is not the case. But for this simple example, it is the same. If you have n coupled springs, and if springs are, I mean, there's certain time period, free spring constituted in such a way that the motion is periodic, then forward motion and reverse motions are equally likely. But these are idealist systems. We do not it's not necessary that real systems will obey this kind of forward and backward motion in an equally probable manner. Okay. So real systems is question mark. Well, in fact, I will show you that it is not the case for quite a few systems. In real life, so time moves one way, right? This is the argument in most books. By the way, there are nice books which I think I put in back. Corral's book is quite nice, and so you can have. I mean, I cited here, but there are thousands of books written. Well, not thousands, at least hundreds of books written on arrow of time. And there are million papers. I mean, this is too many papers. So time moves one way. As I said, our life goes in one direction only. And the seminar, it all. I mean, you can't reverse the seminar. It goes one way. So the question is, this is asymmetric. In real life, we find asymmetry, and what causes this asymmetry? So one solution, which is told often, is second law of thermodynamics. And how is it told? So if I confine the gas molecules in one part of the room and I basically let go, then it fill up all parts of the room. I mean, both the parts of the room. So, and reverse is possible, but is kind of very improbable. You have to wait for long enough time for it to come back to this. So this is entropy increase, So the second law is that entropy will increase. System goes from order to disorder, and that leads to arrow of time. That is what is arrow of time. Okay, this is one sample. There are other ones also, like chaos theory also is told that sensitivity to initial condition is one such cause. I'm going to come to that with some examples. And as I said, these are not. I'm telling. I mean, this is known from Boltzmann time, and that's what 150 years around. So let's revisit aging process. Okay, so this controversy, So why don't we become younger? Now look, if you just look at this fundamental aspect which we are trying to discuss. So this is a cartoon. So I'm young here, maybe some 1 year old. Then I come to this age. Now you want to go back. How will you go back? By fundamental forces. That's where the contradiction comes. There's quite a bit of hand waving which happens. And I think I just want to, I will also still hand wave, but I'll show you the contradiction. So if I want to, I mean, what do you mean by reverse aging? From physics perspective, okay, not from a genes perspective. If you want to, from young, you want to become a toddler, then you take all the molecules of your body and give the reverse velocity. Like this pendulum, where this missile is going back. Now, of course, this has to be done if you want to get here. Also, the air which I'm breathing in right now, that also has to be reversed. So that physically you have to do all that process, all the process in the cells you have to reverse, and even then is unlikely that you're going to reach here. There are many factors which are happening every time. All the processes have to be reversed to come from here to there. So it's really not possible to go from age 50 to age 4. So there is no really contradiction, because you have to reverse all the particles right now, and also things were, well, basically I don't exist in isolation. I talk to other people. Other people also have to be reversed. And there are molecules in the room which I breathe and so on. So all that, in fact, simply is not possible. We can't really say this is a paradox. It's not really a paradox, because these are not a ball. That is what I want to say. In theoretical physics, I'm a bit critical. I mean, I'm sorry, I don't mean to be kind of talking like an egotistical fellow, but either we deal with very point particles, or at worst we say symmetric rigid particles, rigid spheres, or infinite particles which are in equilibrium. In between, we don't really pay. Yeah, please.
MKV, Saurabh here.
Yes, please, sir.
Can I interrupt saying that, this time reversal is an anti-unitary process, operator. The operator is anti-unitary. And in physical processes, it doesn't, you cannot go back from a fully grown man to a toddler in real life, because these anti-unitary operations do not hold.
Okay.
Is there a way to say that?
Okay, you can say from equation perspective, I'm trying to, in fact, I just want to bring in the macroscopic point of view, in fact, intuitive point of view. Actually, by the way, if you say anti-unitary, you look at Schrodinger equation of a particle, no? You're not bringing in more particles.
Yeah.
You deal with multi-particle system. In fact, where is open system? So
yeah.
I think that description needs to be compounded with more features.
Okay.
So right now I don't have those equations here, which in fact I really don't know Schrodinger equation, but I know Newton's laws, you know. So from that classical physics, from there I can see that there is definitely no way you can go from there to there. Even, well, basically it's not a system with n fixed particles, and even if it is n particle system, I'll show you some more examples in next slide. Reversing is not possible. Okay, that is what. Now, so basically, I think when you have, you say, well, things reverse or you want to reverse, we have in mind that there is a lot of spring connected together, oscillators, which are at some point we just, well, basically, my idea is if you want to go in a simplistic way, this hand waving argument, you can say that forward motion and backward motions are equally likely, as I said, for pendulum. Then you say, well, in my life, why don't I have this reversible process in my life itself? It may be some aspects of my life. That is probably a meaningful question, and maybe some of it, like I go to my office and come back, you know, that kind of, I can say something like that. Some of it is reversible, but whole life being reversing is a meaningless. You can see from, if you just pay attention to n particle system macroscopic description, there's no paradox per se, and those questions are ambiguous. To say that 45-year-old will become 4-year-old, it's not possible. Okay, it doesn't really require a big argument for that. Now let's look at some more examples. Okay, I want to say this karma theory. So these are connected again with multi-particles. No, I mean, there are effects which are not only me, you know, there are other people who affect me. So you have to reverse everything, and that is basically a karma network, and it's impossible to reverse them. That's now. So more ways to make symmetries. So I will just list some of them. They're all macroscopic description. Nonlinearity, which I will explain. Well, everybody knows about it, but I will give some examples. Forcing, structures, and friction. These are 4 systems, 4 ways. Okay, so let's look at some more examples. Now let's look at this 3-body problem. 2-body problem, Kepler solved it. In fact, there's reversible in time. 2-body problem. But let's put a 3rd body. So you can just imagine Sun and Jupiter, which are heavy objects, and go in the rotating frame of these 2 objects, and think of a 3rd planet, which is tiny planet. Okay, remove, like Earth can be thought of a tiny planet, and solve it. So this was, in fact, major problem done after Newton. Okay, Poincaré solved, gave some ideas about this problem, 3-body problem. Anyway, here, in fact, is a nonlinear problem. Now, what do you mean by, what is meant by time reverse? Is this time reversible or not? Well, it's a gravity affected problem. So it is time reversible if I reverse the velocity precisely. But precise reversal is not possible, like what Poincaré said. If you have any error, even in 100th decimal place, that will magnify. Okay, and that is one reason for one of the reasons given for time symmetry breaking. Okay, so that's nonlinearity here. We can also put a forcing, like oscillator. Unforced oscillator is symmetric in time, like pendulum. But as soon as I put forcing in the pendulum, then forward motion and backward motion are not symmetric. In real life, we have forcing all the time. You know, tell me a system which is not forced in real life, including quantum systems. Like cavity is forced, hydrogen atom, there is some light shining all the time. There is no single hydrogen atom. So forcing is there all the time, and that breaks time reverse symmetry. In fact, this by theory, I mean, you can just look at oscillator, put force, T and minus T are not symmetric. Now let's look at, we thought about projectile, no, nice projectile going forward and backward. Now just imagine a cannon. a Beaufort's gun, is sending forward shell. Now, if I want to reverse it, what will I do? I reverse the velocity. Will it go inside the cannon barrel? Of course, there is some chemical process. There's some blast as well. Am I going to be able to reverse that blast as well? So this particle thing, we just sometimes overdo it. Again, my critical part of my things are coming out. We should not overdo that. Okay, what we understand using particle dynamics can be applied to the whole universe. That's not true. So I just make a missile. Now just imagine a missile being fired from this structure. Will it come back? No, it won't. So structures can spoil the arrow of time. This is a simple example. So for these problems, one can say, well, of course, reversal nobody does. So what is essentially told that are there natural systems which are equally likely forward and backward? It turns out that most systems are not equally likely both forward and backward. And that is what is breaking the arrow of time. Okay. And all these are not single particle, two particle, is multi-particle structures. These particles are not spherical objects or not point particles for sure. So that's where all these things come. So friction. Now, I talked to a particle physicist, well, some of you are among them. And myself, said, well, friction is a dirty force. Friction has no fundamental origin. I will show you that it has a fundamental origin, according to me. Okay. Now I'm unpopular for my statement, but please bear with me. I will try to show it. Of course, you will not believe it, but I will just put my argument. So let's assume that friction. Well, that I will come a bit later. So friction naturally breaks the time difference symmetry, right? Because if in vacuum it goes back and forth. Well, both are equally probable, but with friction you can't reverse. You cannot revert the trajectory. Okay, now this is the main topic I want to say. I can make it more mathematical. Like I think Saurabh was saying, let's try to make some more concrete argument. These are qualitative arguments, but I think qualitatively correct arguments. I would like to say that some of these arguments which are definitely correct. I would hope so. I convinced you that they are well founded on basically logic, nothing mathematical, but it is logical. Now, but I will try to make it more mathematical from turbulence. Also, it gives a nice insights into quite a few things like friction and equilibrium also. Equilibrium I will not talk today, but equilibrium is another very interesting thing which we discover from these equations. But I will discuss on friction a bit later. So let's take turbulence as an example. And I believe quantum turbulence or quantum systems also one can make certain extrapolation from here, not one-to-one, but one extrapolation. I think so. So these are called Navier-Stokes equation. This is a fluid description. So gas in the room is basically made up, of course, molecules, but is a coarse grain. I take 50 of them and you make a point for 50 particles, and there's a certain macroscopic velocity field. Everybody knows in this audience. I think most of you are faculty, as I saw. So this is a velocity field for the gas and is affected by the pressure gradient and viscous force. There's a viscous force, new viscosity here, and external force. So I have all the ingredients which will break the arrow of time, right? The external force and there's a viscous force. I assume for this talk that flow is incompressible and is turbulent. That means the nonlinear term is much bigger than the viscous term. Okay. Now there are certain interesting laws for this, which I will use one of those laws. So this one simulation which shows that it's a really multi-scale. We have structures which are large structures. This vorticity field, magnitude of vorticity field, and there are small vorticities here. But this is again a different topic. So I wrote these two books. I'm advertising it here. I think Pankaj knows about them, but I discussed quite a bit of the energy flux in this book. Okay, now let's go to turbulence. So energy supplied at large scales, so it's multi-scale system. So I take a cup of coffee and I stir with a spoon, Then I supply energy at large scale, which is cup size of the cup. But that energy supplied at large scale goes into small scale, which is basically the molecular scale. It just goes down and it heats up the molecules. Finally, the temperature is higher once the kinetic energy is transferred to thermal energy. But the scale to scale transfer is a non-equilibrium process. And it turns out Kolmogorov showed that I supply energy at large scale here. And it, well, before Kolmogorov, this qualitative picture is known before Kolmogorov. So we go from large structures with large eddies or large vortex to smaller vortex, it goes down into particles. Okay. Now I define various scales here. So basically, this is what is thermodynamics, these particles. And that is basically where we 10 micron or well 10 nanometer or so, that scale, or 100 nanometer. And this is something like centimeter or tens of centimeters. So that scale, this part is non-equilibrium and this part is equilibrium. Quasi-equilibrium is getting heated up, so it's quasi-equilibrium. And thermodynamics works only here. Thermodynamic description is not good for this part at all. Okay, what Kolmogorov showed is reasonably simple derivation, that the energy, how they are distributed at different scales, that is the formula for by Kolmogorov. And he said that if I look at the intermediate scales, smaller than the forcing scale, the energy cascade is constant. I mean, energy is going from 10 centimeter to 5 centimeter to 1 centimeter. The same energy is flowing down. It's like a pipe, but instead of water, you're supplying energy at different stages of the pipe. Okay, so I think I'll skip this stuff. Yeah, so let's come to here. Now, according to Kolmogorov, if I look at 2 points in the field, these are 2 points and difference between the velocity field. Okay, so of course velocity field is a vector. So the 2 points, I should have drawn a picture, but 2 points separated by distance r, take the component parallel to r vector. So that will be a scalar, and take cube of this, and I'll get this formula. This was derived by Kolmogorov in 1941. Now this epsilon u is the energy dissipation rate or energy going down the scale. Now how much time I got? Okay, so let me just tell this briefly. What is this cascade? This cascade is an interesting thing. Huh? So it's not like cascade in this flux is not like a Poynting flux in hydrodynamics or flux of photons coming crossing the surface. So the best example I can think of is energy supplied by the central government to state government. This is a multi-scale from center to state, state to district, district to villages. So there are more and more people who get the energy, but every stage, if there's no corruption, then money flow must be constant, and finally should reach the villager or small consumer. So that is the cascade, and that is what happens here. So you can think of the central government, like that. So it goes down the scale. So this epsilon u is what is a flux which is cascading down, and this is a formula for intermediate scale. Now, how do you get the time asymmetry? Now imagine that I have a velocity field of all the coffee structures, milk structure in the coffee. This coffee fluid. Now, if I compute the delta U cube for the coffee, take any 2 point, compute that. This formula is valid. That means it should be a negative quantity with L will be the separation between the 2 points, and the epsilon U is measured is a heating rate of the coffee per unit time. How much heating is being done, right? Now just imagine the reverse the velocity field of the coffee molecule. Then what will happen to this object? Now it was negative, but if I reverse it, then it's a cubic quantity, so it becomes positive. So if I reverse it, then it becomes a plus sign, because epsilon U is positive and L is positive. So the reverse velocity field will give me if I apply Kolmogorov theory, then say, well, what am I getting? I'm getting some junk here. So the velocity field in the coffee cup is organized in such a way that I get always the negative sign. If I reverse it, I will not get a negative sign. Then I know that the reverse velocity field are not the real velocity fields. It's a reversed, or is not the correct velocity field, and that tells you that forward motion and backward motion can be differentiated and by this formula. Or in the reverse velocity field, the energy will flow from small scale to large scale. It will go other way around, from common man to the government. Well, I mean, it can happen, but no, I mean, that doesn't happen that way around. So from reverse velocity field is not possible, only forward velocity field is possible. You can see from this law. It's a mathematical way to say this, that energy cascade is giving us an arrow of time in this. In fact, it's possible. So normally, now just to dig deeper, if I change the velocity of the molecules in the room or in a thermodynamic system, you cannot differentiate between forward velocity field and backward velocity field by just looking at a snapshot. But it turns out if you look at velocity fluid description, then we can differentiate by if I measure the flux. And its weight, there are ways to measure the flux. I can measure this epsilon u even mathematically. Okay, that's what we do in our computational simulations. Okay? So this is the energy transfer, which is always from large scale to small scale. The reverse velocity field will be going from small scale to large scale, and that breaks the time. In fact, so this is what is telling us, no, that in real life energy goes from large scale to small scale in non-equilibrium systems, which is forced and which has a dissipation. I hope I am not losing you all. Like earthquake, the energy supply at large scale, large tectonic plate, and it goes down to small scale and it goes down like that. In crack propagation, the energy is given at the, when you tear a paper, energy supplied at large scale that goes down to small scale. So there are tons of examples, like a sun is heating the earth, and that earth is basically going down the small scale, finally going to leaves and heating the molecules of water and so on, of air. So there is certain direction almost all the time in 3D systems in forward direction. Okay, so this is, so energy transfer is has certain direction, and it is not possible to reverse it. If you reverse it, is unreal system. That is not possible. Okay, of course, this is all because of friction. No, this is all because of friction. So in fact, very interesting thing is arrow of time in a for a gas. You need to compute entropy at two different times. And if entropy increases in the second snapshot, then it is a real time, real system. But if entropy decreases in the forward time, then you can say that it's not the correct. In fact, it's not correct flow, or well, it's not correct physical experiment. You need two different time for the gas, but for fluid, one snapshot is enough. Okay. Anyway, so I think I will skip this again due to lack of time. This is a Fourier description, and this also tells us a little bit more quantitatively, but I think I'll skip this part. Okay, so looks like problem is solved, right? So in hydrodynamic systems, there is an arrow of time which can be determined by the flux. So just to summarize, I take the velocity field, and by our mathematical formulas, which I described by Kolmogorov theory, that delta U cube, or with Fourier description, we can compute the flux. If flux is positive, then I know that it is a real system. If flux is negative, then it's time reversed, if you are giving me the reverse flow. And we can contrast it. In the projectile problem, you could not contrast it because both are equally possible, forward and backward. There's no way to contrast, but in turbulence, it is possible to contrast. Or not only in turbulence, but like earthquakes. Energy does not flow from small scale to that big tectonic plate. Okay, or so in fractures, energy flows from large cracks to small cracks, not other way around like that. Okay, but viscous dissipation is an issue. So how do we understand viscous dissipation? Now, the idea is the following, okay? So the fluid, which like my water, so is made of particles that follow fundamental forces. Ideally, I can just make this, I can just look at all the molecules which make this water and don't shake it up. Don't apply this stirring. You let it be. In the beginning I rotate it, but I let go. So at t equal to 0, I have given enough energy, but let go. Then what is the total kinetic energy? Total implies sum of kinetic energy of all the molecules. Now that kinetic energy must be constant, right? It's isolated system because I don't force it now, and total kinetic energy is constant. So what happens? What is heating it? So heating is nothing but, if you look at this picture, so well, I'm sorry, I should remove this external force. I had energy in this large flow. So please ignore this black arrow. So there's energy in these large scales that goes down to small scale. True, but it's like these large structures lose energy to small structures, and that goes to particles. So we are transferring energy from coherent flow structures to particles, which is thermal energy. So what is viscosity doing? Like, in fact, is derived in Wright's book. The shear flow is, the viscosity in the shear flow is taking energy from the shear energy or shear kinetic energy to particle kinetic energy. So what is viscosity doing is transferring the coherent energy to incoherent energy. It's basically accumulation, I mean, basically some kind of coherent or large scale energy goes into small scale energy. So viscosity essentially does that, nothing more or nothing less. And this is the origin of dissipation. The dissipation is not a dirty force. It is there in macroscopic description. In multi-scale systems, most of the time we'll have dissipation. As soon as you have large scale structures, small scale structures, there are certain accumulation in some region. Well, in all 3D, well, many 3D systems which I look at, we have this phenomena, large scale to small scale accumulation, and that is dissipation. And it's not only in turbulence, but we have earthquake, cracks, fragmentation, Earth's environment, as I said, like sun heating the Earth, it happens. In quantum, there's something called superfluid turbulence, which Pankaj works on. There is dissipation, and that goes from superfluid to normal fluid. Even for pure superfluid, there is a coupling from large scale flow energy to phonons. Okay, and I believe cavity as well. So quantum decoherence is a major problem, and I think this multi-scale description could be a useful way to entangle this, disentangle this, if you look at different scales. In biology, so there's a biological arrow of time. That's a big problem. Now, for me, if you look at it in one way, we take energy from food and oxygen, and that's go to dissipation. And this gives the arrow of time. It's not that dissipation generates food. It always one way. And so biological arrow of time is solved. And if you look at asymmetric arrow of time, so viscosity is real or dissipation is real. We need it in systems. In fact, we should not overemphasize the fundamental forces. We should bring in these aspects, and that will make our understanding richer. Multi-scale, different, and transfers, and that's what can solve quite a few problems, I believe. Okay, now I think past work I will skip, and I can just make one remark that, like, some of these works are motivated by Boltzmann ideas. We are within turbulence, we are looking at particles of turbulence, and then see forward, backward, how they're different. But what I was trying to do in my earlier description is energy transfer at fluid structures, large scale structures, small scale structures. So that is the difference, and that is, I think, also one may try in other systems like quantum turbulence and earthquakes and so on. So there is an exception which was also bothered me and some other people. So two-dimensional structures, two-dimensional turbulence. So it's also real, no? Like soap film or rotating turbulence has certain two-dimensionality. It turns out energy goes from small scale to large scale. Like hurricane formation is an example of 2D turbulence. Hurricanes are formed, this large scale structure, which is originated from small scale structures. And of course, energy feed is by this moisture. You know, they feed, they connect. Well, basically, they give energy to this structures, and they combine. Here, the structures combine and they lead to large scale structure. And it turns out here again, this energy flux is a good idea. It's just that the energy flux is negative sign, and you can work it out. Things are okay, no problem. And I believe this could be the idea for creating structures. Like under gravity, now of course that will be a different problem than what I discussed right now for rotating turbulence. We don't put gravity there. So gravitational forces can lead to large scale structures just by dynamics. In fact, it does lead to large scale structures. Planets are formed that way, stars are formed that way. And inverse cascade could be a good way to understand those aspects. And entropy is not well, basically the problem comes when you start thinking in terms of entropy. And I don't want to say that entropy is wrong, but this dynamics is a nice way to look at this aspect. So cosmological error of time. If you look at some books, they'll highlight this to be a problem. So evolution. Universe is evolving, and suppose I want to have a collapsing universe. So oscillating universe. So expanding universe, then it comes it comes back. Now, if it collapses, then entropy will decrease, right? Or this black hole collapse is called. And that is a problem. No, second law will be violated. But I do not look at second law. I look at energy transfers, and this inverse cascade is possible under at least 2D turbulence or gravitating system. And that could be a clue saying, well, don't think of entropy, but think of these cascades, and then structures are possible, and there's no problem. I mean, we have examples where structures are formed and no issues. Okay, I'm running short of time, so I think I should close early. So close quickly. So causality is not highlighted in modern descriptions of arrow of time, but I think it's quite important. Like I said about karma stuff, no. So this was quite important in the past. A causes B, and that is the arrow of time. You know, it's not the B. B doesn't cause A. So that is also a nice way to do a arrow of time. And I think it is important. I mean, we should bring it back. That is what I would like to say. Okay, now mirror symmetry. I think I have 3 more slides. Pankaj is okay. 5 more minutes. Or
yeah, it's fine. Yeah.
Okay. So this is a one leaf. It is a fruit, in fact. I saw in during this spring season, and this is left-right symmetric. No, this one. Now it turns out it breaks into 2 parts, and both of them take this shape. Now this is breaking left-right symmetry. No, this is one example. I mean, I kind of like this, so I took a picture and I'm just showing you here. So what causes left-right symmetry? Breaking of left-right symmetry. Is helical? Is definitely not left-right symmetric. So symmetry is broken, and it's because the drying, this side dries differently than the other side. Is other thing is wet. I believe simple things like drying can help. Why it is twisting, like wood twists because of moisture and different differential drying. Now, I'm not trying to look at it from microscopic perspective. What is weak nuclear force is doing here, or even electrodynamic force is doing here. I bring in environment, just idea of drying, and then this breaks it. So this is trivial. I mean, I think my heart is in the left. Is because of many factors which brought the heart to the left. Now asking that why my heart is in the left, it's okay. I mean, this is not a big problem. If you think of many like this twisting is I could easily argue for that. So what I meant to say is that environment plus system breaks the symmetry is easily explained here. We don't need to resort to fundamental laws for explaining this. Of course, sometimes it's very useful. Like I'm told that the chiral materials are very important these days in condensed matter physics, and I think this is all very important research. But we no need to go to that fundamental equations to explain everything. That is what my main point of view here today. Now conclusions. So let's just go a bit slowly. Multi-scale description helps understand breaking the time reversal and mirror symmetry. Okay. So in these examples, I did not invoke, in fact, didn't have much equations. It's multi-scale description, qualitative, energy transfers are invoked. So, but there are other things like friction, forcing, nonlinearity, structures. I didn't write it here. I think they're important. And asymmetric energy transfer. I think this is a nice framework which is useful to say what breaks the symmetry. Also, what I'm more interested in this dissipation comes naturally in this framework. We don't need to be saying what is the origin of friction. By the way, this static friction is also nice way to see it in this framework. Block moving on a table. So there are coherent motion of the block. Now it goes into incoherent motion of the molecules at the interface between block and the table. So that is what this friction is doing. Of course, there is complicated physics involved at the interface, but it's the same framework which is working here in the static friction or dynamic friction as well for the block sliding on a table. So this is also universal framework from multi-scale perspective, and so as I said, this origin of dissipation is what I really I think is a byproduct of this. So we can generalize this to other driven dissipative systems, and it could possibly address biological and cosmological error of time. To me, is logical, but of course other people can object. And these are some papers which I wrote with quite a bit of difficulty. So this is published in EPJB, and these are some transactions of Indian National of Academic of Engineers, and the popular articles are there in my website in the front page itself. These are multi-scale. I describe quite a bit of it in this popular article, and let me just make this. Just because I faced a lot of difficulty in getting this paper published. So first is ridicule, the idea, in this by Schopenhauer, and second is violently opposed, and third, in fact, is a tragedy that is accepted as self-evident. It's obvious, that's what is told. It's obvious that is true. Okay, with this I stop, and I thank you for your attention. I'm sorry I ran over time, but I hope it's okay. Okay, Pankaj, it's all yours.
So thank you, Professor Verma, for nice talk. Now floor is open for questions.
So shall I unshare it now, or keep it? I'll keep the slide right now in case there's a question.
Yeah.
Okay.
MKV, I think it's a fantastic idea. I mean, basically the first line of the conclusions is very, very sort of appealing to me, that multi-scale description actually helps understanding the time reversal and the mirror symmetries. I'm surprised that you had difficulty in convincing people. and the way you went ahead, it's convincing. It's quite convincing.
Many thanks. Actually, I don't know why people kind of. I had 10 rejections for that paper, EPJB paper.
Yeah, referees are funny.
Yeah, but thanks a lot. Thanks for this compliment. You know, it's I think it's just that people find it okay. This is unusual and it's wrong. That kind of thing.
No, it's very out of the box looking at things, right? I mean. That's what I feel. I mean, as you were speaking, I was just, trying to think that how would this come about? That is this multi-scale description, which would, aid in the understanding of these fundamental symmetries. That is something very interesting.
Thanks a lot. Very thanks, Saurabh. Yes.
The students,
any other question, comment?
The students should ask questions. I think this should be understandable by
Professor Alika Khare. Professor Alika
Yes.
Khare.
Yes,
Yes,
just
Alika.
on yeah, your last slide, the thank you slide, has forced me to just share something on a non-technical lighter part.
Okay.
In your time reversal example, you took the one example of the energy transfer, energy distribution from the government to state, district, and village, and then you said that it is non-reversible. That means from the villages and the home it cannot be. But nowadays in our country, in some of the states, including your UP, it is possible, particularly if you have installed the solar panel and you are generating your own electricity, and if it is surplus, you can transfer back to the government. You just have to put your meter which can go in both the directions. So that you can surplus electricity can be transferred back. Just don't do the lighter side.
Yeah, no, I think it's an interesting example. Yes, it goes into grid. Also, banks. In banks, people put money, savings, and that gets collected in banks. Yes, so these are kind of inverse cascade. This going backward, multi-scale way. Yes, so yeah, grossly I was telling that most of the thing flows from large to small, but it's true that like money or electricity can go backward. Yes, I agree with you. Thanks.
Yeah, this is on lighter note only.
No, it's correct also. It's also
non-technical.
It is technical. I wrote a paper on this money flow. Well, it's in the book chapter. But if you bring in bank, then it is a reverse process. So it is technical. I mean, but to keep all these factors, it just it kind of makes it more complicated. That's why I didn't say that. But it's a important piece for full understanding of economics, which I hope people do it anyway, I think, but I don't know how. But I just want to make one more remark. In economics, a lot of models are motivated by Boltzmann kind of picture. Then they try to bring in interaction as a approximation. So that's what I made a remark. I think I'm quite confident about my remark that in physics, we either focus on one or two particles or infinite particles with an equilibrium distribution. Now, in between, of course, people work. I mean, non-equilibrium is there is huge amount of work going on, but it is not still a main framework. I think we need to bring that as in the main blackboard. This is could be a main plank for our understanding. So a lot of, by the way, there was a paper by Mingna Saha, first paper where economics, he tries to say that the natural money distribution is Gaussian, by saying that each person is a actor like molecule. That's kind of So that is
that is because they follow the random distribution, and the random distribution is a Poisson distribution or it is a Gaussian distribution. So that is the reason that they always follow the distribution as the Gaussian distribution or the Poisson distribution.
In reality,
some of the cases they go even for the higher order of movement also.
Actually, reality, it is far from Gaussian. Gaussian is the only small scale. At a consumer, well, basically at a poor people level, but the rich people are basically, there's a power law, and there's called Poirot distribution. So there's huge. In fact, this Gaussian is only a very small part of the economic distribution is Gaussian. Most of big range is non-Gaussian, and that has to be to do with this energy flow, this money flow. I can send you this paper if you like.
Yeah,
I don't.
sure, please.
I will.
Yeah, I would like to read it. So
Yeah.
you know my email ID, so
Yeah,
you
yeah.
can please.
I will.
Yeah.
Yes.
Okay, thanks.
Thank you.
MKV, do you have a version for the Kramer's degeneracy in this description? I don't know how to connect it. I mean, I don't remember what the degeneracy exactly is, but if there is if a system obeys time reversal symmetry, then the positive and the negative, the energy states come in pair and things like that. I don't exactly, I mean, there are lots of these things. There are lots of conditions. So does the, in the Fourier space, or in the energy space, does this, the multi-scale says anything about this Kramer's degeneracy? It's called as probably Kramer's theorem, I forgot.
Okay, I think I will discuss with you, Saurabh. I'm not, I don't know about this theorem. So I think I vaguely remember it is to do with eigenvalues of the systems, which if time was symmetric, but okay, let's discuss it after the talk.
Sure.
We can just stay after the talk and yeah. Okay.
Okay. Any other question? Remark?
Hello, I have a question. Am I audible?
Yeah.
Yeah. Professor Verma, I just wanted to know that you said that the arrow of time is determined by the, the flux or the energy cascades. It basically requires the dissipation, or it requires non-equilibrium macroscopic systems. I just wanted to know, like in microscopic systems, we at least, or in theoretical physics, we have an approach towards the understanding of the nature of time. In this, is it only that the arrow of time is determined, or the nature, or the nature of time is determined? Like, for example, in this case, is time also just a parameter, and you have a direction of the arrow of time, or is the nature of time understandable from this theory?
No, this theory is time is parameter for me, or which time is more like a d by dt of the Schrodinger of the PDE. Okay, I assume time is there, which is like Newton's law. So this is all in classical framework, where time is same for all reference frames. There's no relativity involved in this. So time is in the Newtonian framework. I assume that there's absolute time for every observer, and that is assumed here. So this is not about origin of time. This is not how to do it. But systems go one way in time. That is what I try to emphasize. Most of my talk was, of course, concentrated on the flux, but things like structures, that is not to do with the flux, and that can break the forward and backward motion. Time reverse motion, I want to rule out time reverse motion for macroscopic objects. That is what my objective is. So friction is one way. I mean, this is a natural thing which is told in textbooks, in all textbooks. Friction breaks the arrow of time. But I just listed a couple of more, which is also very similar thing. I hope I'm clear. Is it? So,
yeah. Thank
you. Yeah.
Yeah. Any other question, remark, comments? So I have one question that in the inertial range, you showed that the flux is negative. So it basically shows you the forward cascade of energy. But even in the inertial range, you have friction. Friction is very small, but you do have the friction. So that will break the symmetry of time, no?
So friction is okay. So let me make it clear. Once you say friction, then anyway naturally breaks the time. Okay. Now this description is more of a quantifying flux and what signatures does it have on the arrow of time. For example, given a velocity flow, can you say that this is a real velocity field or not a real velocity field? Okay, this is like quiz question. So given this, I can give you a snapshot of 3D velocity field. I'd like to ask whether it's a real field or is it time reverse field. Now, how will you answer this question? So I want to basically play this mathematical game in this part. So the question is, if it is reversed, then this delta U cube will be positive. In the real if it is real field, then the delta U cube will be negative, okay, for inertia range L. Here, by the way, I did not put the viscous effect. Huh? There is a viscous effect term which is plus some more term that has been ignored. Viscous terms is small compared to this 4 by 5 epsilon L. Okay, and viscosity is acting at all scales, but is weak in the inertia range. Okay, Pankaj. So I'm just trying to amplify the role of dissipation and this energy flux idea. But yeah, so is more of writing the second chapter of this idea. This is not this. Well, yeah, you understand. I'm just expanding that. If I just say friction breaks the dissipation symmetry in the turbulence, is like obvious. Okay, fine. What else? So I just went deeper, and it gives you deeper insights. That's what you agree with that statement?
Yeah, it's fine.
So, and also we can try to look at entropy. So entropy is not well defined for turbulent flows. So we have been trying to cook up a formula for entropy. So what is entropy for this? So this entropy increases. For how do I define how will I say what increases for? Because this entropy there's no delta Q. Well, I can say that there's heating up things at the particle level, but I can I don't want to deviate now from this talk, but I can turn on the viscosity. And we turn on the viscosity, then also we can define arrow of time in the early phases at least. Okay, and that is the theory of all this discussion about equilibrium, non-equilibrium. That's another game. But if nu is 0, then what is delta Q? Right? Is delta Q is not 0 in fact. You agree with me? So delta Q by T is the delta S, and that is 0 for Euler flows. Then how will I define arrow of time?
Yeah, I got it.
So basically, just dig deeper in this game.
Yeah.
So this is a technical talk. This topic for a technical talk. So I didn't want to.
Yeah. So thank you, Professor Verma, for such a illuminating talk and giving the various perspective of this multi-scale phenomena. And so with this, we would like you to thank you again for delivering this colloquium. And we thank our technical team for helping us to take care of the talk. And with this, I would like to thank you all for active participation. And our next colloquium will be next week on topic I'll just convey to you in due time. So see you all next week.